Hello, I will show you how to use motion simulations and then the Excel sheet made by our Tetra OptiMotion team, how to extract the system properties of a mechanism. And for this demonstration, I will be using this simple slider crank mechanism, and the general approach of our demonstration has been visualized here by this figure. So it consists out of 3 steps, and this approach uses the general torque equation formula, which is depicted at the top. So I just want to stress out that we don't have to neglect the second term, because this is a system with variable inertia. So the approach of getting our system properties has 3 steps. So the first one, we will exclude gravity and apply a constant speed to our mechanism, and then we will see that in our torque equation, the first and the last step will be 0, so only the second term will be active. For the next step, we will include gravity and apply also a constant speed. Then our first term will be included. And for the last step, applying a constant acceleration and also excluding gravity, we will use this one as to determine our initial inertia variation. So I will stress that in a little while, that we only will need the initial time sample. But first we have to make a few decisions. So what is the machine range, the desired resolution, and the reference frame? And for that I will go over to our motion simulation. So the first one, machine range, determines how far our motor can turn. But in our example, we can make a full circle, so 360 degrees. So our machine range can make a full rotation. But it can happen that if your mechanism is not allowed to make a full rotation, you have to decide, okay, I can only turn by 90 degrees or 180 or a custom value. But in our case, so one full rotation is possible. Then the resolution determines the output, so how accurate you want this graph to be. So on what is the sample rate of this graph, and in our case we will use 1 degrees as a uh, as a resolution. And the last one, so the reference frame, is from where we want to start by rotating. So we will start from this initial position. All right, so let's get to it. You can see here that the motion simulation is already been built up, so this is not the focus of this demonstration. So, and then we have the 3 solutions. So the first one, as been seen in the approach, is where we exclude gravity and apply a constant speed. Okay, I think this Windows. Oh, all right. So for the fixed number of steps, we will choose 360 and a solution end time of 36 seconds. Meaning, if we apply a constant speed of 10 degrees per second, then we will make a full rotation in 36 seconds. And then if with 360 steps, we will have a accuracy of a resolution of 1 degree. Okay, so if we have a look at our driver, we will see that the constant speed of 10 degrees per second has been applied here. All right, so let's solve the first solution. All right, and now we have to export our results. And our result, which is the input in our Excel, is always the torque which has been measured here at the point on where the motor would be mounted. Okay, so this is the torque which is measured with the joint. So just to show you, this is the relative torque dz from this joint. But I already made a graph object, so this is ready to be exported, or maybe I'll show you the plot first. So yeah, this is the result of this first solution. Now we have to just export it to a spreadsheet. Alright, and so we copy and paste all of these values into our Excel, and then you'll see that the Excel just converts the torque from Newton millimeter to Newton meter. Alright, so the first solution has been done. So let's do the second one, and we'll see at the top here that so for the second step we will include gravity and also apply a constant speed. So let's make this one active. And you can see that we included Earth's gravity, and then all the other settings are exactly the same. All right, and again, but maybe I'll just close up the first export, and then we can export to spreadsheet again. Copy and paste all the values into our Excel. Just want to mention, if you've chosen another resolution instead of the 1 degree and you have more samples, then you can just drag the last values here until you include all your values. So, and now let's do the third step. Close this Excel. Then you'll see that he automatically switched to the driver with the constant acceleration. And if I'll open this one up, then you'll see this is a constant acceleration with the value which corresponds to the one that we have defined in our Excel sheet. So keep in mind that all the settings that have been made regarding the sample and also the simulation time have to be exactly the same here in the Excel as in the motion simulation. Alright, so for the last one, we will only need the first sample, because this one determines the initial inertia. Alright, I'll just double check. Okay, the Excel has been closed. Export to spreadsheet. And as mentioned, we only need the first sample. And then we'll copy and paste this one at the last table. Okay, and that should be it. So if I look over here, then we see our graphs for our system properties. We can get the values over here as well, but this is a graphical representation, and at the third tab in our sheet we have also a overview. Okay, so I hope you can use this Excel sheet onto your systems